Okay. So in general, as we said, in the two graphs in true stress and true strain and the engineering graph, nearly the elastic region points are common. This is why we can find the elasticity from both. Okay. But if you want to be very accurate, it will be you will have a little bit difference because true stress and true strain are different from engineering stress and engineering strain. But since the difference in elastic region is negligible, then the elasticity models can be defined from both graphs. Okay, but in general, the initial definition of elasticity is from engineering graph. Okay, now the importance of the true stress strain curve is that it can allow us easily to find the start of necking. Why? Because we will see together that we can determine what is the form of equation in this zone. Okay, this zone is called the flow curve, and we will learn together that its equation is given from it is of this form. It is k uh, so sigma is equal to k times epsilon to the power n. Okay. So since we have here, we know the type of equation, we can find k and n graphically. And we can determine 2 points of the flow curve and then calculate the corresponding value of k and n. And once we do this, if we extend this graph, we can see a separation point. The separation point between the flow curve, this is called the flow curve, if we don't have necking, okay? And if we compare with the actual curve, we can see a separation point. The separation point between the two is the necking, is the start of necking, and is corresponding to the maximum load, F, okay? So as we have seen in the previous session, in engineering stress, sometimes the maximum is not very clear. This is why, while in the stress strain curve, if you do this method, you can determine the point of start of necking. And the point of start of necking will correspond to F maximum. Okay, so if you measured the corresponding true stress and you deduce the value of F maximum, you can calculate the tensile strength by F over A0. Okay, so this is a graphical method that will allow us to determine the starting point of neck. Okay, and this can be done by drawing the curve, the flow curve projected as if necking is not taking place. So after finding k and n, you draw the curve and you extend it beyond necking, and then you compare with the actual graph. You will determine a certain separation point. This separation point corresponds to your starting point of necking. Okay, so this is how we use the true stress strain curve to determine the starting point of necking. Any question on this? Okay, so let us continue. Strain hardening and stress strain curves. We note that true stress increases continuously in the plastic region until necking, which is like, if you want, this is the same behavior in engineering curve. In the engineering stress strain curve, the significance of this was lost because stress was based on the original area value. What do they mean by this? They mean by this that the engineering curve is not really the stress. It represents the variation of the force, not of the stress, because it's always divided by the original area. While the true stress curve, okay, really shows the variation of stress, okay, because in this graph, the actual stress is represented, which is the force applied over the actual area of the specimen. Okay, so if you want, in summary, the engineering stress is a representation of the force variation, while the true curve is representative of the variation of the stress. Okay, because the engineering one is not the actual stress, since it does not divide by the actual area, but it is proportional to the force. It is the force over a constant, which is A0. Okay, so this is why they are saying here, the stress is really presented in the true stress curve, not in the engineering curve. Now, how we can say from the true stress curve that the metal is becoming stronger as strain increases. Why? Because as strain is increasing, okay, before the necking part, what is happening is that the specimen is undergoing a higher stress. Okay, so this zone we call it the strain hardening zone. Okay, this is called this part. Okay, it's called the strain hardening zone because in this part, okay, our specimen is undergoing a higher stress. Okay, strain hardening zone. Okay, of course, after necking, it's different. Okay, so the strain hardening zone is before the necking part. Okay, now how we can use the true stress strain plot in order to determine the characteristics of the strain hardening zone. Okay, so let us, if we do the plot together, uh, a good idea is to do the log-log plot, because if we try to do the log-log plot, we will see that we have a linear variation. Okay, why? I will tell you why. Because we have seen together, we have observed that the true stress versus the true strain engineering, the true strain is of the following form: sigma true is equal to k, which is a certain coefficient, times epsilon true to the power n. Okay, so if we apply the log on this equation, what do we get? We get that log of sigma t is equal to, if you apply log to a product, what do you get? You get log of k, which is a constant number, okay, plus what? Plus log of epsilon to the power n, okay? And what is log of epsilon to the power n? You know that from log properties, log epsilon to the power n can be replaced, this term can be replaced by n times log of epsilon, okay? So if you plot log of sigma true versus log of epsilon true, you will have a linear variation, okay? Because it's a constant plus n times log, okay? So this is a linear variation. This is why we say that if you want to determine, an easy way to determine k and n is to draw on a log-log scale the different points. I will have a linear variation. In this case, n, this coefficient, okay, can be calculated as the slope of the linear part, okay? Please don't confuse the linear part in the true curve and if you don't do log-log, if you put the true curve, then it will be in the elastic region, you have a linear phase, but in the plastic region, you don't have a linear phase. The linear phase here that you obtain is for a log-log plot. Here, we didn't present the elastic region. We are just presenting points after the elastic region. Okay. Now we will see after that you can represent on the whole scale log-log presentation. If you do the log-log presentation on the whole scale, you will also obtain a linear profile in the elastic region, but the slope will be higher. In the elastic region, the slope is higher than in the plastic region. Okay, so if I just put the points in the plastic region, I can determine n by the slope of the curve. So it's here a over b. While if I want to determine k, okay, k will correspond to true strain equal to 1. Because for true strain equal to 1, okay, what will happen is that log of 1 will be 0, and then log of sigma will be equal to log of k. Okay, so here this is why this point for epsilon true equal to 1 will correspond that the true strain will be equal to k. Okay, so if you draw on the curve, log 1 will correspond to the point of log k, and you can determine then k. So this is a graphical method to find n and k. And we will see together in next session other methods to find n and k. Any question on this? Okay, so we are done for today and we continue next time. Bye bye.
Thank you.